Now in this lecture we will define the total derivative. Total derivative is actually a generalization of the derivative which we have studied in the case of single variable function. So in case of several variable, directional derivative is not actually the generalization of the concept of derivative or the concept of differentiability, because we have seen that if several variable function has all its directional derivative, even then the function is not continuous. But in case of one variable, if a function is differentiable, then it is continuous. So we will generalize the concept of differentiability of one variable and introduce a new definition, total derivative, and that total derivative will actually have this property that if the total derivative exists, then all the directional derivative exist, all the partial derivative exist, and the function is also continuous at the point where the total derivative exists. So now let us recall the concept of derivative in case of one variable. Suppose f is a function from R to R and c is some real number. So we define the derivative of f at c by f dash c, and f dash c is defined as limit h is going towards 0 f of c plus h minus fc upon h, and we say that the derivative exists if this limit exists. Now the problem in case of several variables is that if we write the definition like this, then we have to write c plus h. Here the h is a real number, but in case of several variable the h has to be a vector, and we have to divide by h. So we have to divide by a vector, but we don't have any concept of dividing by vector. We don't know how to divide by a vector. That is not defined term. So we cannot define in case of several variable the definition of derivative like this. Okay, so what can we do? Now consider a new function ECH. Now I am introducing a function ECH, f of c plus h minus fc upon h minus f dash c. So what is f? F is a single variable function. So now in place of defining it in like this, in case of single variable, now I am going to define the derivative in another way. So what is that way? So for that I am going to define a new function, and that function is ECH. ECH is fc plus h minus fc upon h minus f dash c. So I am explaining the derivative of single variable in different way. Now we take the limit h is going towards 0 in both the side. So in place of this limit h is going towards 0 we write, and here also I write limit h is going towards 0 f dash c. Now by star means the definition of f dash c, this whole terms will become f dash c if derivative exists. And here there is no h, so this will again turns out to be f dash c, and their difference is 0. Okay, so it means this ECH, when h is going towards 0, is going towards 0. This ECH is called error terms. This ECH is called error term. So as soon as this h is going towards 0, this ECH will go towards 0. Now, so this double star can be written as f of c plus h minus fc. So h you will multiply here. So f of c plus h is equal to fc plus h times f dash c plus h times ECH, where this limit ECH is going towards 0. Now introduce a map TC from R to R as TCH is equal to h times f dash c. This TC is a linear transformation. If you consider R as a vector space over itself, then this TC is a linear transformation. And this map TCH is completely determined by this value f dash c. So for each coefficient f dash c, you will get a linear transformation. So now, up to now, we were saying that this f dash c is actually the derivative of f at c. In place of this, we will call TC the derivative of f at c. TC is completely determined by this number f dash c. So this linear transformation, now the derivative or differential coefficient or derivative of a function is replaced by a linear transformation. So in place of f dash c, we will call TC to be a derivative. And now this definition can be easily extended to the case of several variable. So now what is the difference? Till now we know that f dash c is a number. Now the derivative is a linear transformation. And we will define the derivative in case of several variable with the help of this second formula. So for several variable, suppose now f is a function from a subset S of Rn to Rm. This is a function and C is an interior point of S and C is some interior point of S. The function f is said to be differentiable at C if there exists a linear transformation Tc from Rn to Rm. So Tc is a linear transformation from Rn to Rm. So what is Rn? Rn is the vector space in which the domain was contained, and Rm is the vector space in which the range lies. Now, so TC, so we call a function f to be differentiable if there exists a linear transformation Tc which satisfies this condition, and the condition is f of c plus v is equal to fc plus tcv plus norm of v up into ecv. What is norm of v? Norm of v means the length of vector v. So that is under root v dot v, and this limit v is going towards 0, ecv is equal to 0. This ecv is the same, this ecv is the error term. Okay, this is the definition of differentiable. This is the definition of derivative or total derivative. So Tc is called the total derivative or derivative of f at c. So in place of a number, now the derivative is a linear transformation which satisfies this property, and we are not going to prove, but it is proved that, or it is a fact that if a linear transformation satisfies this equation, then that linear transformation is unique. So derivative is unique. So any linear transformation which satisfies this equation will be the derivative of function f at c. And of course this ECV may be different for different functions. Yes. Now come to the example of single variable, and in that case, what is derivative now? So suppose f from R to R is defined as fx is equal to x square and take a point C is equal to 2 in R. Then f dash 2 is equal to 2x, which we know till now, and its value at x is equal to 2 will be 4. This is what we know till now. So what we know is not wrong, but now we have generalized this thing to a linear transformation. So now onwards, by a derivative means a linear transformation. And what is that linear transformation? That linear transformation is map Tc from R to R as Tc of x is equal to x into f dash c. So we have multiplication by f dash 2 is a linear transformation. So f dash 2's values is 4 as we have calculated just now. So this is Tcx is equal to 4x. So because c is equal to 2, so you may also call it T2. So this is a linear transformation, and this linear transformation is actually the derivative of the function f. Now we know that a linear transformation is completely determined by its matrix with respect to fixed basis. So matrix of the linear transformation, that is derivative, the matrix of the derivative with respect to a standard basis is called Jacobian matrix. And we will do more examples for this derivative function after doing the Jacobian matrices. Now before that we will do some observations. So we will do the observation in the next lecture.